Today's lesson is about the von Neumann architecture, and we're going to learn the names and the purpose of all the components in the von Neumann architecture so that we can describe how a computer works to run programs, surf the internet, play games, all the things that you do on a computer, smartphone or tablet. And that's going to be split into us answering these 4 questions by the end of the lesson. We need to know what are general purpose computers, and what is the stored program computer model, which is also known as the von Neumann architecture. We need to know what is the FDE cycle, and I'll explain what that is in a second, and what are the components used in the von Neumann architecture. So what are each individual bits, and what is the purpose, what is the function, what is the job of all of those components, and how they work together to fetch a computer program. So all modern computers work on this architecture that was suggested by a mathematician called John von Neumann in 1945. In that, what happens is split into 3 parts, and the computers are doing this cycle continuously. This cycle we call the fetch, decode and execute cycle, the FDE cycle. And what we are going to do today is focus on the fetch part. And what happens in the fetch part is the computer goes and gets a computer program from memory or storage device and brings it to the central processing unit in order to execute it, to run it. So let's start with a bit of history. In the 1930s and early 1940s, computers had started to be invented. This is a very early computer, and you can see it's pretty large. The way computers worked back then, if we wanted to change anything that they did, was we had to, say for example, we wanted to add a number instead of subtract a number. What would happen is you'd need to flick all of these switches to write the program to decide what you wanted it to do. And if you wanted to change one of the numbers or part of the program as well, you would switch these wires around until it was put them into different holes, so it would change the data, the number or the word or the letter that the computer was trying to process. And this was operated largely by women and men, going through and changing all of these different bits every time they wanted the computer to do something different. These computers had a specific purpose. They could only do certain things. And this, although saved a lot of time adding numbers and working things out, took a lot of time to set up and weren't very practical things other than arithmetic. Then in 1945, a mathematician from Princeton University called John von Neumann suggested in a paper something called the von Neumann architecture, which is what computers still use today. It's called a stored program model. And this is the first computer that Princeton University created in about 1952. And this followed the architecture John von Neumann wanted. You can see the switches have largely gone, and so have a lot of the wires. What they've been replaced with is these disks at the bottom of the screen, which save a program to them. The computer then here accesses those disks depending on what you're telling it to do. If you wanted to change the program or change the numbers, you would need to change these disks at the bottom. Now this saved a lot of time because it meant that you could save these disks, take one out, put it somewhere else, and then bring it back and use it again later when you wanted it to be used. And these now have been replaced largely by hard disks, USB sticks, and as we move into the era of the cloud computing, which you're using now. And this then led the way to what we now know as modern computers, or what we now know as general purpose computers. And we call them general purpose computers because we can use these computers to perform anything that we can compute. All we have to do is change the program stored on the disk or in memory, and then the computer then uses that program, the one that's been written by a computer programmer, to tell it how to process the information. We can also change the data that's being used, and you'll see this when you're perhaps playing on your games console or your computer, that when you want to change it to a different game or to do a different thing, you load up a different app or put in a different DVD or Blu-ray, which stores a different set of instructions. So now let's have a look at the von Neumann architecture. How does this actually work, and what are the main comparts of it? So as an overview, all modern computers have a central processing unit. That is essentially the main hub of the computer. It does all the calculations. It controls all the different parts of the computer. Then all modern computers have what's called primary memory. This is where programs and data of the applications you're currently running and using are stored temporarily. And this normally is split into two parts. One is cache, which we'll look at in a future lesson. And what we're going to focus on today is main memory, which in modern computers is known as RAM. And then what we also have, which von Neumann suggested, is that we have what's called a secondary storage. And this is to store programs when the computer is off. Main memory loses its information when you turn a computer off, so we need somewhere where we can save our programs, save our Word documents, save the progress in our games or websites and pictures. And that you might know as things like hard disks, DVD drives, USB drives, cloud storage, and many other things that you can store information on when the computer's off. And you probably use these every day. He also suggested that these components be joined together by a set of wires, which are called buses. And these allow the information, the data, the binary information to move from secondary storage into primary memory when you open up an application, and then from main memory into the CPU when it's actually working on that program. These buses are really important, and we're going to look at some of the specific ones used today. So as I said, this lesson is based on the fetch section of the fetch, decode, execute cycle. And for that, we can remove a lot of this information and focus just on the CPU and main memory. And these two buses here that transmit data to and from the CPU and main memory. Now, to begin with, we are going to focus just on main memory. Main memory is split into lots, hundreds, thousands, in fact billions and trillions in modern computers of sections. Each one can store a binary number, and that binary number, each section is given a number which we call an address, so that if we wanted what was in this section 5 here, we would tell main memory to go and fetch the binary number that is in address 5. In main memory, when you load up a program or start the computer, what we do is we load in a lot of binary numbers which are instructions. These are the things that are going to tell the processor how to run our program. We also load in data. And the data is binary numbers again, but it stores the information that the program, the instructions need in order to be able to load our program. And that might be, say, a Word document, it might be a number we're using a calculator, it might be the progress of our saved game, it might even be the information that needs to be displayed on a website. Each of these is a binary number, and we normally try in main memory to keep all the instructions together and all the data together and the programs together as one, because you might have more than one program open at once. You must have the operating system, Microsoft Word, Android, iOS, open. So when the computer turns on, its first job is to load the instructions and data from the operating system. So now what we're going to do is just a quick check that you've understood what's come before. And what you need to do is read the descriptions on this left hand side here and match them to the key phrase on the right here. So what I would like you to do now is pause the video, match up the descriptions with the key phrase, and then unpause the video when you're ready to go on. So pause the video. Good, so now you've finished, unpause the video. If you haven't finished, pause it again. And now let's go through the answers. So a computer that is capable of performing many different functions by changing the instructions it stores in main memory is a general purpose computer, which most modern computers are now based on. Stores the binary data that makes up the data and instructions of running programs. That's main memory, and the key part there is that it's in the running programs. If they're closed programs, they're stored in secondary storage or they're not running. Each location in memory is identified by an address, which was the numbers that we saw. The name of computer design used by modern computers, named after John von Neumann, is the von Neumann architecture. Long-term storage of programs and data when program is not running or the computer is off. So secondary storage, your hard disk, your USB drives. Cache and main memory are collectively known as primary memory, and we've looked at main memory so far. And CPU stands for central processing unit. Now if you got most of those correct, so if you got say 5 out of 7, then it's okay to move on. If you got less than 5 out of 7, go back to the beginning of the video and have a look at the video again and try this again. So now that we've understood what the different parts of main memory are and how they're split up and used, let's bring back the central processing unit and the 2 buses that join main memory and the CPU. We're going to focus now on the different components and purpose of those components inside the CPU. Inside the CPU we have about 6 or 7 bits of small memory, each joined together by buses, which we can see shown by the arrows. Each of these small bits of memory is called a register. Each register has a special purpose. They are really small and always located inside the central processing unit. And each of these bits of memory has a specific purpose. It does one job. And that job is part of the fetch, decode, execute cycle. Today we are going to focus on 3 of these registers. We're going to focus on the program counter and what its purpose is. We're going to focus on the memory address register and what its purpose is, and we're going to focus on the memory data register. You are going to need to be able to identify which of these, which each register is eventually. And the way we're going to do that now is just by looking at them each in turn. The program counter is the start of the fetch, decode, execute cycle. It may not always be located in the diagram in this top left hand corner, but what it would always have is one arrow, one bus coming out of it, which points into the MAR. The MAR, memory address register, sends an address to main memory, and it will always have out of it an address bus going in one direction to our main memory. So the way we identify the program counter is we find the MAR, which has the address bus coming out of it. Remember, one directional arrow which goes to main memory or RAM. The program counter has no arrows going into it, but a bus coming out of it into the MAR. The MDR, or memory data register, has the easiest way to identify that is it is connected to a bus which has 2 arrows on it, which go to the main memory. So it has 2 arrows joining the MDR and the main memory. The point of this bus is it sends data to and from main memory, so it needs to be in 2 directions. Let's have a little bit of a closer look at how these work together now with inside the fetch, decode, execute cycle on the fetch part of it. Okay, so before we move on, let's check that you've understood how you can identify each of the registers and components from the CPU and the two buses that are used in the fetch part of the fetch, decode, execute cycle. So what I'd like you to do now is pause the video and to decide on the names of all the items labelled A, B, C, D and E shown in this diagram. A bit of a tip, I would start with the buses because they'll help you. So pause it now, and when you're ready, unpause and check the answers. Okay, so now you can unpause before we check the answers, and if you haven't finished yet, make sure you pause before we move on. So as I said to you, let's start with the buses. Now the first bus, or the top bus, we're going to identify here, and the way to look at it is how many arrowheads it has. Now this one has 2 arrowheads, meaning that binary data is sent both ways. In which case, because it's sent both ways, that will send both data and instructions from the main memory, which would be over on the right hand side. So that is the data bus. The one below, the red arrow, has 1 arrowhead, so that means it is only sending binary data from the CPU to main memory, which would be over here. So that means it's only sending addresses and is the address bus. Now we've got those 2 buses labelled, what we can do is start to label the registers. So the data bus sends instructions and data to and from main memory into the memory data register. The CPU uses the address bus to send addresses to main memory, and therefore this register here will be the memory address register, and the memory address register finds the address of the next instruction that it needs from the program counter. So if you got 4 out of 5 there, I would say you're ready to move on. If you got 3 or less, then what I would do is go back and watch the last part of the video again. So now we know what the components are as part of the CPU that are used in the fetch part of the fetch, decode, execute cycle. Let's look at how they work together. Let's bring back memory with our instructions and data and our address bus and our data bus. We can get rid of the registers that we don't need for the fetch part, which are used in the execute and decode part, which we'll look at in a different lesson. And the whole purpose of the fetch part is to get the instructions from main memory and load them into the CPU in the correct order. So we're actually not looking at the data either yet. That comes along in the decode part, so we can remove the data from our model at the moment as well. So let's look at each of the purposes of these registers and how they work together. When we load up a program, the first thing we need to do is get the first instruction from main memory into the MDR, so the processor can decode it and execute it later on. The program counter stores the address of the instruction that we need next. So when we load up a computer or load up a program, the program counter has copied to it the address, the number of the memory location of the instruction that it next needs. So when we start up a program, the first instruction we need is instruction 1. So the address that instruction 1 is in is copied into the program counter. The memory address register stores the address of the instructional data that we need from the CPU next. So a copy of the program counter is sent to the memory address register. Once that copy has been sent to the memory address register, the program counter increments, adds 1, so it's pointing to the next instruction, ready for it to be told that we need the next instruction once we've finished processing the first instruction. Before we can get onto the second instruction, we need to process the first instruction, and that means fetching it. So the first part job is the memory address register sends the address down the address bus to main memory. Main memory then makes a copy of the data, the binary instruction found in that address, in this case 1. Once it's made the copy, it sends that copy back down the data bus back into the MDR, and the MDR stores that instruction ready for it to be decoded and executed, which we're going to find out in the next lesson. Once it's finished executing, we then need to get the second instruction. So let's have a look at that and make sure we understand the purpose of each of the instructions. Bring back all the other registers and let's look at what's at the beginning. So the program counter stores the address to the next instruction that we need to execute or we need to fetch of the running program, and that's really important that it's the program you're currently using. It sends a copy of that to the MAR and increments so it's ready once instruction 2 has been finished being executed to go and get program 3 so that we never ever stop. The memory address register stores the address of the next instruction or data to be fetched from main memory. So it checks that address and then sends it down the address bus to request that binary number from the address that we're currently looking at, in this case 2. So the address goes down the address bus and then the main memory makes a copy of the binary number, in this case instruction 2 because we're looking in address 2, and sends a copy of that back down the data bus so that it can be stored in the MDR ready to be decoded and executed later on. And this cycle then keeps repeating until we turn the computer off or we get to the end of the program. So let's now have a look at how to answer a few exam questions. When we're looking at exam questions, it's important to read the question properly and understand what the key words are that help you to answer the question. And in this question, outline what happens at the fetch stage of the fetch, decode, execute cycle. The key word here is outline. The reason this is the key word is because it tells you what level of detail you need to go into. This isn't asking you to explain step by step each register and its purpose. It's a 2-mark question, so it's asking us to outline what the overview of the fetch as part of this fetch, decode, execute cycle is. So what we're looking for here is two points to collect the 2 marks. So the first part is the next instruction is fetched to the CPU. So we send the instruction to the CPU that we next need to decode and execute. And that gets us the first mark. And the second mark comes from where we're getting that from. And that's from main memory. So they're really nice 1-sentence answer with 2 key points outlining what's happened and really paying attention to that key word. So in this question, again, we need to read the question properly and identify not only what knowledge it's asking for, but how, the key words that say how it wants us to ask it. And we also need to pay attention to how many marks there are. So state a component of the CPU using the fetch part of the fetch, decode, execute cycle and describe its function or purpose. So we can see very quickly at the and, it's split into 2 parts and there's 2 marks. The first mark, state a component of the CPU using the fetch part of the fetch, decode, execute cycle. State is a keyword where we just literally need to name what part or name a key part of the question. So we looked at lots of components and the picture below shows a few or shows them all, and we could have any one of the program counter, memory address register, memory data register, address bus, data bus, or even main memory, RAM. So just picking one, just listing the name, the program counter gets us the state mark. The second mark to describe its functional purpose. Its functional purpose is its job. So that's again in the video, and if you can't remember it, look back now. But the purpose is that it has the purpose of storing the address of the next instruction of the running program. Very clearly, we've stated what its job is. What does it do? We could be really clever and say that it also has to increment by 1 each time it sends the address to the MAR, the memory address register. And acronyms are fine here. But that last part won't give us any more marks because the red and the green part already get us the marks. Let's have a look at 2 final examples. Our first one, explain how the main memory is used during the fetch execute cycle, and it's 2 marks again. This time the key word to tell us how to answer the question is explain. And explain doesn't mean that we have to state, it's told us what we're talking about, main memory. What we need to do is just write 2 sentences that explain what main memory does. So here are my 2 sentences. Program instructions for running programs are stored in main memory. I've stated the main job of main memory. It stores the instructions of running programs. The next instruction is fetched to the processor from the main memory. So what main memory does is it's every time it's asked for the next instruction, it sends it to the process, to the CPU from main memory, which will get us the 2nd mark. One more question with a different keyword. Describe the steps of the fetch execute cycle. Now this is a 6-mark question, and I'm not going to answer it completely. I'm just going to start you off. So here we need to describe. Describe being the key word. So here we're going to get a mark for saying which component we're talking about and describing what it does, but also linking it to the next part. So the program counter, the first part, the component in our fetch part of our fetch execute cycle, stores the address to the next instruction of the running program. It increments by 1 every time it sends an address. Now that's very similar to the question beforehand. Explain how memory is used during the fetch execute cycle. But this time we need to add a few more parts. The address is sent to the memory address register, which stores the address to the next instruction or data to be fetched from the main memory. That would get us our first 2 marks, potentially a 3rd. But what we would need to do is carry on describing all the different components that we've learnt about in this lesson until we've got 6 points covered off. So now that you've been through the whole video, you need to go and click on the link which you can find in Show My Homework on this PowerPoint, which I'll attach, and complete all the questions on this topic using the online form. And the introduction video shows you how to do that. Please remember to put your full name in and what form you're in. It won't show you the answers at the end, but what I will do is send you the answers the following week once you've all had a chance to do it.